Hey folks, so we're continuing on with 6.3 in complex numbers, and we just did a few operations with complex numbers. Now I'm going to show you how you would graph a complex number. So remember how we would graph a point, and I'm choosing a point, a nice one. I'm going to do an example here. If I wanted to graph 1 square root of 3, and we're just going to guesstimate. So I would just go over on the x-plane, xy plane. This is just the real number plane. So I go over 1 and then 3. It's not quite 2, so it's just, right about there, 1, 3. And we can play around with it. It's like this point. I'm using this general example, and I'll show you how we get that in a second. But I could drop, remember, the distance from the origin. This would give us a certain angle here, and we would drop the perpendicular here. So I'm going over 1, so this leg is 1, and this height is root 3 from this point that's given here. And I could find the hypotenuse by doing 1 squared plus square root of 3 squared equals c squared, the hypotenuse. And if I solve that, I find that c is equal to 2. So I have all this information. I could also calculate this angle right here to find it, which would just be, I'm going to just use the tangent. So the tangent of theta is equal to the square root of 3 over 1. In your calculator, we'll stay with degrees. If you do tan inverse of the square root of 3, that equals 45 degrees, and you can check that. You should check that on your calculator in degree mode. So it's actually not 45 degrees, so if you checked it, you would realize I'm wrong. It's 60 degrees. So that is actually 60 degrees. So this angle right here is 60 degrees. That's theta. All right. And so that's how we've been exploring the XY plane. So now what if we take this, kind of something similar to this, 1 square root of 3, and I graph it. In this case, this was our x, and this is our y, and this is how I'm going to compare it to this and try to show you how it's equivalent to this in terms of the trig functions. So a thing similar with x and y would be 1 plus the square root of 3i. Okay, so this is your real part. If you remember, this is your imaginary part with the coefficient of the square root of 3. So what you do when you graph a number like this real part is on the x-axis, this imaginary part is on the y-axis. Okay, but it's got the scale of I. So I go over 1 because that's just the real part, and then I go up, and it would be not quite 2, so somewhere around there, and that's root 3i. So here's 1i, here's 2i, okay? So this is root 3i if you think about it. So this would be 1 plus square root of 3i, okay? And we can still drop down this perpendicular, and we still get an interesting angle, and the x and the y, notice that they're the same. So there is the theta still is 60 degrees, that angle, okay? And there are some connections we can make here. The first being, if I look at this angle right here, I can say then that cosine of 60 degrees, let's go back to this triangle right here. So the cosine of 60 is adjacent leg on that triangle over hypotenuse, 1/2. Okay, so that implies that 2 cosine 60 equals 1. Remember, the 1 is your x value. Okay, so that's what x is. It's not times x, it just means that that's what x is. So the next one would be the sine. I could say that the sine of 60 is equal to the square root of 3 over 2. So that implies that 2 sine 60 equals the square root of 3. And remember, square root of 3 is your y value. Maybe that will make more sense. So if I look at this, here's my x part right here, and here's my y part. So I'm going to substitute in those in terms of sine and cosine. So remember what 1 is equal to from here. Let's do that in green. 1 is equal to, from, where is that equation? Right here, 2 cosine 60. So I'm going to substitute this in. This is equivalent to 2 cosine of 60 plus, what was the square root of 3 equal to? 2 sine of 60. So that's 2 sine of 60, but now I have my I value there, times I. And I doesn't go on the inside with 60, it stays out. So what is 2? Well, look at the triangle over here. Can you think about what 2 is? 2 is equivalent to R. Okay, so that's this right here. And I can factor it out. So it's 2 cosine 60. And what they do, just to make sure that the I doesn't get stuck inside, is they put it out front. I sine of 60. Okay, so this is equivalent to that complex number, which is x plus y I. That's what we had in this form. And our specific number was 1 plus the square root of 3i. So I'm saying that the 1 plus square root of 3i is equal to this value right here. So here is the little green box. For any complex number, we can translate that to z equals r cosine theta I sine theta. Remember, r was our 2, just to make that connection. Cosine was our 60, and sine was 60 as well. Okay, and our complex number was 1 plus the square root of 3i. So this was our x value, this was our y value. And then to find theta, you have to set up a triangle and in the xy plane, and that will help you. This is called the modulus of z, which is what the radius is, or the r value, okay? But remember, we're in the complex plane, so it's the modulus of z right there. And a short way to write this right here, and they say it in the book a little below, is it's equivalent to writing RCIS of theta. And that's just kind of a nice quick way. So because you're assuming it's cosine and sine, the I is the imaginary part. Here's cosine, here's sine, and then you put the angle and whatever R is, or the modulus of z. Notice that it is the square root of the two legs, x squared plus y squared. Okay, and theta is the angle, or they say the argument of z. Oh, and there it is right here, r CIS theta. Okay, so if we have to translate a complex number and put it into trigonometric form, this is number 26, first identify what x is. So x is equal to negative 3, remember that's the real part, and y is equal to negative 2. That's the coefficient of the imaginary part, an I. Now you have to figure out what the modulus is, or r, and that's what we're familiar with, the r value. So you graph this point, negative 3, and then I'm going down negative 2. And remember, this is, we're in the complex plane now. Remember, this is the imaginary axis, and this is the real axis. So, but I still gauge it the same way. I go over negative 3 units, and then I go down 2 units. So negative 2i units here. But I can still calculate, and you can look in the book and they'll show you how and how it's related. But this is the modulus of z is finding this value, r, or we can call it. Yeah, so this is 3 units. We're going negative 3 and negative 2. And if I square that, it's 3 squared plus 2 squared. Notice I don't even include the negatives, equals r squared, or the square root of r. So we have 9 plus 2, or plus 4 is 13, equals r squared. So r is equal to the square root of 13. And remember, that's always positive. So that's the square root of 13 right there. This helps us when we're thinking about what quadrant. Remember, we're in quadrant 3 now. Okay, so this is, we need to find an angle that's in quadrant 3 and make sure it is. So to find what your value is, we're going to look at the tangent of, let's just call this angle theta here. Okay, so tangent of theta is equal to opposite 2 over adjacent leg, which is 3. And if we do this in our calculator, make sure you're in degree mode because it'll just make it easier. So you check your mode. Yep, in degree. So I'm going to do tan inverse of 2 divided by 3. Now I get 33.7 degrees. And as you can see, that's not going to be in the third quadrant. That's in the first quadrant. Because remember, by symmetry, 33.7. So we would also have a triangle with 2 and 3 here. So this angle is 33.7 degrees. So how would you find this angle? Well, we need to add 180 degrees. So theta is going to equal 180 degrees plus 33.7 degrees. And that should equal, let's see if we do our math right, 213.7 degrees. So now I found my theta, which is 213.7 degrees. I know my x value, I know my y value, which helped me find my r value. So r is equal to the square root of 13. So once you have your r and your theta, all you have to do is use formula 6.3. So from 6.3, I can say that my complex number, that negative 3 minus 2i, is equal to square root of 13, quantity, cosine of 213.7 degrees plus I sine of 213.7 degrees. And you can see why the shorthand 6.4 from 6.4 is a little nicer to write it. So that's equivalent to the square root of 13 CIS 213.7 degrees. And remember, that means cosine of 213.7 degrees plus I sine of 213. Okay, so this is our equation, or it's our number written in trigonometric form. Okay, so to convert this into trigonometric form, it's okay for the real part to be 0. Remember, this is of the form 0 plus, it would just be negative 1i if we looked at this form, right? Because there is no real part. So that means that x is equal to 0 and y is equal to negative 1. And so if you draw this, where are you? So you're down here at 0, negative 1. That's easy to find the angle because it's all the way over here, which is 270 degrees. So that tells me is all the way down here. So that tells me that theta is equal to 270 degrees. So I have theta, and it's pretty easy to find r because remember that's the distance from 0 from the origin, and that's 1 unit. So r is equal to 1. Okay, so this is equivalent to r quantity cosine of 270 degrees plus I sine of 270 degrees, or shorthand is r CIS 270 degrees. Either one is completely fine to write it. And remember, that's the negative I is equal to all of these. Okay? So this number I wanted to show you because you have to prove just a couple of identities. So this would have fit better with 6.3a lesson. So we're going to kind of go back. I wanted to show you some operations. Remember what proving an identity is. You start with one side and you try to get to the other. And it's best to just identify or let each of these complex numbers. Remember, Z1 and Z2, these stand for complex numbers. So I'm going to say let Z1 equal A plus BI and Z2 equal C plus DI. As long as we could say this, be official, A, B, C, and D are real numbers, we're okay. And we're kind of assuming that. So let's first start with Z1 plus Z2. And this is actually good that we're doing it today because it's a good refresher. Well, what does that mean? You just add the real parts together and you add the imaginary parts together. So we have A plus C as our real parts, plus, and then I'm going to just do a little shortcut, B plus D as my coefficients of the imaginary part, and then factor out that I. So now what we're going to do is we're going to take, given this, we're going to take the conjugate of z1 plus z2. And remember, z1 plus z2 is this number, z1 plus z2. So the conjugate of that says you take the real part, a plus c, you don't change it, the sign of it, and you take the imaginary part, b plus di, and you don't change that. The only thing that you're going to change is the sign. So since it's plus here, it's going to be minus here. And then after that, you just do a little cleaning up. So you have a plus c minus bi. I'm going to distribute this negative and the I to both of these terms. So it's minus bi minus di, and I'm going to regroup. So now I have a minus bi and plus there, because c is positive, c minus di. Now notice what these are. These are the conjugates of z1 and z2. So remember, z1 was equal to a plus bi. So over on the side, we could write then that the conjugate of z1 is equal to a minus bi. And the conjugate of z2 right here is equal to c minus di. So we just found that because this is the conjugate of z1 plus the conjugate of z2. QED. So we started here, remember, and we got to the second side. And then we're done proving our identity. Okay, so the book does a really nice job in deriving de Moivre's theorem. We're getting to the end of this class, and at this point I would say please look at it, and it's pretty interesting, but I'm just going to show you how to apply it. So what's neat about de Moivre's theorem is I can raise a complex number to any power n that I'd like to, and we can actually find the value of it, because believe it or not, it's kind of like this -4 gets to go to the radius, which is, remember, this is your r, and then it squeezes into here, so it's times this angle theta right here and here. So remember, just from looking at this complex number in trigonometric form, I can say that r is equal to 3 and theta is equal to 14, and n is equal to -4. So to calculate this, I can say that this is equivalent to 3, which is my base r, to the -4, so I'm doing this part right here, quantity cosine -4 times theta, which is 14, plus I sine of -4 times theta, which is 14 again. So once you find one of those values, you don't have to find the other. So remember what a negative exponent does. It's 1 over 3 to the 4th, which is 3 to the 4th is 81. So it's 1 over 81. If I clean this up, it's cosine of -56 degrees plus I sine of -56 degrees. Most of these angles are not in this form where you have a negative. So think about where -56 degrees is. It's somewhere in quadrant 4. So if I wanted to find, so here's -56 degrees, if I wanted to find all of this, do you see that I would just take 360, subtract 56 degrees from that, and that grand total gives you 304 degrees. So it would probably be best, and I'm going to clean up 3 to the 4th, as with writing this as cosine of 304 plus I sine of 304 degrees. And then remember the shorthand would be 1 over 81 CIS 304 degrees. So we just raised a complex number to a pretty high power, and thanks to de Moivre's theorem, we can actually calculate its value pretty quickly. Now we can also use de Moivre's theorem, and that's what I'm going to show you next. And this is the last example on how to find the roots of a complex number, which is a big deal. It's actually listed as one of the objectives for this class in trigonometry, so I just had to show you. So we are able to find the roots of any complex number, and in this case, a root back in the real plane. Remember, if you had something like, I'll do it over here, like a cubic, the roots of a cubic would be all of the zeros. So here's a zero, here's a zero, and here's a zero. And I didn't even tell you that complex numbers, believe it or not, even though they say they're imaginary, they're very well used in engineering and in the real world. And in differential equations, you'll see them a lot because it's kind of bizarre and crazy, but you can take some kind of crazy equation, you can put it into the imaginary world, into the complex world. You can do all your manipulation and work, and then you can convert it back to a real kind of situation and apply it to our real world and our tangible world, our life out here. So it's pretty fascinating. So there is a need for this in the use of roots, finding roots, and understanding complex numbers. So if I were to find the cube roots of this equation right here, this formula, only works if it's in this form, the trigonometric form. So that's the first thing that we have to do is we have to convert it. So remember, x is equal to the square root of 3. Y would be the coefficient of I, and since there isn't one, you can put a 1 there. So we're going to say that that's 1. And remember, we also have to find theta. So put that x, plot the x and y. Sorry, that's kind of crooked. They're both positive. So I'm going over root 3 units and up 1 unit here. And if I calculate the hypotenuse, well, you don't even need to calculate the hypotenuse. Oh, yes, you do to complex. So you need to find r. So remember, r is equal to the square root of x squared and y squared. So it's 1 squared and square root 3 squared. So you have 1 squared, which is 1, plus square root of 3 is just 3. So it's square root of 4, which is equal to 2. We did something very similar to this earlier. So you have that r is equal to 2. So far we have r equals 2. Now to find theta, you can use tangent again. So the tangent of theta, here's my theta, is equal to opposite over adjacent, which is the square root of 3. And in our calculator, we're going to do tan inverse of 1 over the square root of 3, and that will give us 30 degrees. So we can say that theta is equal to 30 degrees. So now I've got theta, and so my number here, my complex number, so I can say the square root of 3 plus I also is equivalent to r, which is 2 cosine of 30 plus I sine of 30. Now, this formula is derived from De Moivre's theorem because that told us how to raise a complex number to any power of n. And if you solve it, you can find that to find all of the roots to solve like something greater than that, it's r to the 1 over n. And you can look at the proof in here and how they find it. You can look online. There are a ton of videos on YouTube about how to prove this theorem. But all we're going to do is we're going to plug in the number. So I'm going to show you how to use this for k equals 0, 1, 2, and n minus 1. Now if they say to look for the cube roots, cube would imply that we're looking for the 3 roots there. So for k, our k is going to be equal to, we're going to do 0, 1, and 2. Because remember, 2 would be this n minus 1. Because n is equal to 3, we're looking for the cube roots. 3 minus 1 would be 2. So I have to do this formula for k equals 0, for k equals 1, and for k equals 2. So what do? I take my r value, which is 2. I'm doing this part first. I'm raising it to the 1 over 3. Do you remember that 2 to the 1/3 is equivalent to the cubed root of 2? Just a little review on rational exponents. You probably learned that in Algebra 2. And then it's going to be cosine theta of whatever the original one is. It's 30 plus 360. Now k is 0 to begin, so for the first root it's just 360 times 0, so it's just your 30 there, over n, which is 3. And then we have plus I sine, and it's the same thing. We've got our 30 plus 360 times 0 over 3. If you clean this up, we've got that this is equivalent to the cubed root of 2 quantity cosine. Now this goes away, both of these, because it's just times 0. 30 over 3 is 10 degrees plus I sine of 10 degrees. So I just found my first root. Now I have to find the other roots, which means I need to make a little more room on this page. Okay, so we just found the first root. That was when k is equal to 0. And like I said, so this is all the work for it. K is equal to 0. Now we have to do for k equals 1. And then we'll do k equals 2 as well. So for k equals 1, to calculate this root, we just do 2. Then I'll go back to green. So we're going to do 2. We're back here. R is equal to 2. 2 to the 1/3 doesn't change that. Cosine, theta is still the same, it's still 30, plus 360 times 1 over 3 plus I sine of, can I just say all of that again, 360 plus 1? That this is the same as this, just due to room. Okay? If you clean that up, you've got the cubed root of 2, okay, and then parentheses cosine, and this ends up being 30 plus 360 is 390. 390 over 3 plus I sine of 390 over 3, which ends up being 130. So we've got the cubed root of 2 times the quantity cosine of 130 degrees plus I sine of 130 degrees, and you could make that even nicer. You could say that's the cubed root of 2 quantity CIS, or you don't even need the parentheses there, 130 degrees. Okay, to find the last one now, for k equals 2, you can kind of see the pattern. I'm just going to do it shorthand because really I need to just find this value, because I know that this is the same. It's the cubed root of 2 because n is 3, and these guys are the only things that are changing. So theta is still 30 degrees, and then we have plus 360 times 2, because that's for k equals 2, over 3. So if we calculate that, that ends up being, I believe it's 250 degrees. Okay, so I can just say then that the cubed root, you get the formula, is equal to CIS of 250 degrees. So this was the second root that we found, and this is the third root of this complex number. And that's the end of this lesson. I hope it was helpful, and come see me if you have questions.